This is part 2 of our module on operational amplifiers. This is what this lecture is going to cover. I'm going to take up additional examples of standard operational amplifier circuits, and then we'll go into the cascading of op-amp circuits. Just to review what we took up the last time, these are the steps in analyzing op-amp circuits. The first thing you have to do is check that there is negative feedback. If there is negative feedback, then chances are your op-amp will be operating in the linear region. So we applied the assumptions for ideal op-amps operating in the linear region, and those assumptions are, first, that the non-inverting input voltage will be equal to the inverting input voltage. No? That's V plus is equal to V minus. And then the second assumption for your ideal op-amp is that the currents flowing to either your inverting input or non-inverting input will be equal to 0. And then we use the circuit analysis tools we are already familiar with to determine the desired quantity. Typically, what we want to determine is the output of the op-amp. And I always tell this to students, when you don't know what tool to use, you always go back to nodal analysis. Finally, we check for saturation. How do we check for saturation? Your output voltage should not be greater than Vmax and should not be smaller than Vmin. If you find that your output voltage is not within the allowable range, then you have to limit it to the allowable range. So we adjust the output accordingly. And after adjusting the output, recompute for whatever the desired quantities are. So these are the steps in analyzing op-amp circuits. So let's apply this to some new standard circuits. Okay. So here is the sixth example. This is that of an inverting summing amplifier. So again, the problem is to derive an expression for the output voltage in terms of the input current and the circuit resistances, of the input voltages. Not input current, of the input voltages. So let me change this now. It should be voltages. And the circuit resistances. Assume the op-amp is ideal. Okay. So what we do is, let's apply Kirchhoff's current law. Where will we apply Kirchhoff's current law to? We will apply it to this particular node. The voltage at this node is V minus. So applying KCL to the inverting input, I'm going to have V minus V1 over R1 plus V minus V2 over R2 plus V minus V3 over R3, okay? So those are the currents here, right to left here. That's the first term, the second term, the third term. We have a current flowing left to right here. That's V minus V sub O all over RF. And we have a current flowing into the inverting input. But we know that that current is equal to 0. Okay, so we don't have to consider that anymore. So this should be equal now to 0. Okay, but remember, we apply one of the assumptions for your ideal op-amp. V minus is equal to V plus. And in this particular case, V plus is equal to 0 because it is grounded. So V minus is equal to V plus, which is equal to 0. So all of these are now equal to 0. Okay, so what do we get? Okay, I'm going to get negative V1 over R1 plus V2 over R2 plus V3 over R3, okay, is equal to V sub O over R sub F. Or, expressing V sub O in terms of the inputs, I have V sub O is equal to negative RF over R1 V1 plus RF over R2 V2 plus RF over R3 V3. So this is of the form negative, okay, let me call it A1 V1 plus A2 V2 plus A3 V3. Okay. Note that if RF is equal to R1 is equal to R2 is equal to R3, I'm going to get V sub O is just equal to the negative of V1 plus V2 plus V3. So that's why you call it an inverting summer. It sums up all of the inputs, okay, then negates it, and that is what will appear at the output. Now, if this condition is not met, then you're going to have to compute for the coefficients A1, A2, A3, depending on the values of RF, R1, R2, and R3. And note that we can actually select a set of values for RF, R1, R2, and R3 so that we can implement any value for A1, A2, and A3. So RF, R1, R2, and R3 can be chosen to implement any value of A1, A2, and A3. Of course, we are constrained by standard values of resistances that are commercially available. I mean, you cannot just go to a store and say, I want to buy a resistance equal to 23 ohms, for example, or 21.5 ohms. There are standard resistance values available. But theoretically, if you can have any possible resistance value, then R1, R2, R3, and RF can be chosen to implement any value of A1, A2, and A3. So that is your inverting summing amplifier. If there is an inverting summing amplifier, there's also a non-inverting summing amplifier. Okay, so let's analyze this circuit. Okay, here we do KCL in two different nodes. First, we do KCL in this particular node. Okay. So this is the KCL in the plus terminal. KCL at the plus terminal. Okay, the voltage at the plus terminal is V plus, so this is V plus. Okay, so you have V plus minus V1 over R1 plus V plus minus V2 over R2. Okay, so that's this current, V plus minus V1 over R1. This current, V plus minus V2 over R2. Then the third current is V plus minus V3 over R3. The fourth current is this current entering the non-inverting input. But we know that to be zero because of our ideal op-amp nature. So this is now equal to 0. Okay, let me try to isolate V plus. Okay. I'm going to have V plus times 1 over R1 plus 1 over R2 plus 1 over R3. Okay, I try to collect all the V plus terms. this is going to be equal to V1 over R1 plus V2 over R2 plus V3 over R3. Okay, so from this, we know now that V plus is equal to, okay, you have 1 over R1 plus 1 over R2 plus 1 over R3. This is raised to the minus 1 because I put it in the other side of the equation. And then now I have V1 over R1 plus V2 over R2 plus V3 over R3. Okay, so that just gives me a relationship between V plus and my input voltages. But what I want is an expression for my output voltage. Okay. I can do KCL here at V minus. Here, this is at V minus. Okay. So what will I have? No, I have, so this is KCL at the negative terminal. Oh, let me put that in quotes. Okay, I have V minus over RA, okay, plus V minus minus VO over RB. And then again, this current, the third current is 0. So this is now equal to 0. Let me isolate V minus. Okay, I have V minus 1 over RA plus 1 over RB is equal to V sub O over RB. Okay, and so V minus is now just going to be equal to, okay, if I multiply both sides of the equation by, okay, let's do it step by step, you know. So if I transfer this to the other side, okay, I'm going to get, let's see, yeah, I'm going to get RARB over RA plus RB, okay, VO over RB. Okay, so this is just going to be RA over RA plus RB multiplied by V sub O. Okay, that is going to be my expression for V minus. Okay, but we know that because this is an ideal op-amp, V plus is equal to V minus. So I can actually equate this term with this term. So what am I going to get? I'm going to get, okay, let's write out this term first, no? V sub O, okay, sorry. Yeah, V sub O, RA plus RA over RA plus RB, RA over RA plus RB, okay, that is my V minus is equal now to V plus. Okay, this is 1 over R1 plus 1 over R2 plus 1 over R3. This is raised to the minus 1. Okay, V1 over R1 plus V2 over R2 plus V3 over R3. Okay. And so finally, I get V sub O. This is now going to be, okay, RA plus RB over RA, 1 over R1 plus 1 over R2 plus 1 over R3 raised to the minus 1. Okay, V1 over R1 plus V2 over R2 plus V3 over R3. So here is another circuit. This is the circuit of a difference amplifier. So derive an expression for the output voltage in terms of the input voltages and the circuit resistances. Assume the op-amp is ideal. Okay, so here again we have a case where we apply KCL twice. We apply KCL to both the non-inverting input and the inverting input. Okay, so let's apply KCL at the plus terminal. Actually, you can also apply voltage divider, no? But let's just do KCL. So you have V plus, okay, over R4 plus V plus minus V1 over R3. Okay, remember again, there is no current entering the non-inverting terminal, so this is now going to be equal to 0, and I can isolate V plus. Okay, I'm going to get V plus 1 over R4 plus 1 over R3 is equal to V1 over R3, or V plus is equal to 1 over R4 plus 1 over R3 raised to the minus 1 multiplied by V1 over R3. Okay, what about at the negative terminal? KCL at the minus terminal. Okay, I have V minus V2 all over R1, okay, plus V minus V sub O over R2. This is now equal to 0. Again, it's equal to 0 because you have no current entering the inverting input. So isolating V minus, I have V minus, okay, 1 over R1 plus 1 over R2, okay, is equal to V sub O over R2, okay, plus V sub 2 over R1. So now I get V minus is equal to 1 over R2 plus 1 over R1. Sorry, I reversed it. This is to the minus 1. V sub O over R2 plus V sub 2 over R1. Okay, but again, imposing the constraints, because this is an ideal op-amp, and that is that V plus is equal to V minus, I can actually equate this to this, no? So that I can come up with an expression for V sub O in terms of V1 and V2. So let me do that, no? So let me write out first V minus. So V minus is 1 over R2 plus 1 over R1 raised to the minus 1. Then I have V sub O over R2 plus V sub 2 over R1. Okay, V sub O over R2 plus V sub 2 over R1. Okay, that is V minus. That should be equal to V plus. Okay, this is equal to 1 over R4 plus 1 over R3 raised to the minus 1 times V1 over R3. No? V1 over R3. Okay. So again, let's do this step by step. So I have V sub O over R2 plus V sub 2 over R1. I now transfer this to the other side. Okay, let's get rid of the negative coefficient, no, negative exponent. No? So this is going to be now 1 over R1 plus 1 over R2, okay? I transfer it to the other side, and this is now going to be 1 over R3 plus 1 over R4, right? Because there's a -1 coefficient. And this is now going to be V1 over R3. Okay. So solving for V sub O, okay, is going to be equal to R2, okay, multiplied by 1 over R1 plus 1 over R2 over 1 over R3 plus 1 over R4, okay, V1 over R3, okay, minus V2 over R1. Okay. So this is our final expression for V sub O in terms of V1, V2, our inputs, and then the resistance values, R1, R2, R3, and R4. Okay, note. If I make R2 equal to R4 and R1 equal to R3, okay, if R2 is equal to R4 and R1 is equal to R3, so itong R1 is equal to R3, itong R2 is equal to R4, you will note that this fraction becomes equal to 1. Okay, this becomes equal to 1. And then this R3 is equal to R1. So I have V1 over R1 minus V2 over R1. I'm going to get V sub O is going to be simply equal to R2 over R1 multiplied by V1 minus V2. The output, okay, is proportional to the difference between V1 and V2, where V1 is the voltage applied through R3 to the non-inverting input, and V2 is the voltage applied through R1 to the inverting input. Okay, so you call this a difference amplifier. Okay, the difference amplifier has actually many good uses in instrumentation. Okay, and you're going to find that out in the future. But just to give you one example, sometimes your voltages, the voltages in your circuit, have what we call common mode noise. In other words, there's a lot of noise in V1, noise or interference, if you might think of it that way, and there's a lot of noise also in V2, no? But these are common mode noise, no? In other words, the noise in V1 and the noise in V2 are common. Okay, what's nice is if you pass it through a difference amplifier, the noise cancels out, no? Because you're subtracting V2 from V1, the noise will cancel out, and what will be left would just be the difference in the useful signal of V1 and the useful signal of V2. So that's the beauty of a difference amplifier. And you're going to see this used a lot in instrumentation where signals tend to be noisy. Okay, so that is your difference amplifier. Okay. Oftentimes we cascade operational amplifiers, meaning to say the output of an op-amp will be used to feed the input to another op-amp stage. And when we do this, we must be very careful to consider the loading effect the input of an op-amp stage might have to the output that it is connected to. In other words, if I have two operational amplifiers, let me just illustrate it in this manner, no? So this is amplifier 1, and this is amplifier 2. Okay, so let's say I connect the output of amplifier 1 to amplifier 2. Okay. So maybe this way, no? Where this is ground. Okay, note that what will the output of amplifier 1 see? No? The output of amplifier 1 will see an input resistance, we call that Ri. Okay. And it is possible for Ri to actually have an effect on the output of amplifier 1. No? Ri have an effect on the output of amplifier 1. Okay. In other words, if the two were not connected, this output will be different from when the two are connected. So it's very important that you consider that. Now, speaking about this Ri, okay, it makes a difference whether your op-amp is, for example, an inverting amplifier or a non-inverting amplifier. No? For example, if your op-amp is an inverting amplifier, okay, so take a look at this circuit. Okay, what did we say about an ideal op-amp? We said that there is a virtual ground, no? There's a virtual ground, or virtual short rather, between your inverting input and your non-inverting input. No? In other words, the resistance that is seen at the input will just be simply equal to R1. No? No? If you're taking a look at the equivalent resistance looking into these two terminals, what you see is the resistance R1. No? So for an inverting amplifier, Ri is equal to R1. Okay. But if you consider, for example, a non-inverting amplifier, so this is your non-inverting amplifier. Okay, what is the current here? No, this current I plus is equal to 0. In other words, this is an open circuit. No? This is an open circuit. So what resistance is seen looking into the input? What you see is Ri equal to infinity. In other words, if I connect this terminal to an output of another op-amp stage, that op-amp stage will not feel anything because this is an open circuit. So that's the importance of input resistance. So let's take an example. Okay. So here I have two. If you take a look at this is an inverting amplifier. Okay, this is also an inverting amplifier. And we already took up what the output of the inverting amplifier is. No, for an inverting amplifier, your gain is, okay, your feedback resistor divided by your input resistance. You make it negative. So the gain of this inverting amplifier is -5. Okay, so let's write that down. No, for this. Okay, for this, your gain is equal to -5. What about for this? No? If Rx is equal to 1K, okay, okay, if Rx is equal to 1K, your gain is equal to -2. Okay, what if the two were disconnected? The two were disconnected at this point. No? What if this connection was not made? In other words, what if we had two circuits here? No? The left circuit and the right circuit. If this is 3 volts, let me call this V1. No? What is the value of V1? No? V1 will be my gain, -5, right? Okay, -5 multiplied by 3 or minus 15 volts. So the voltage at this point will be minus 15 volts. Okay, if that is the case, what is V sub x? What will be V sub x? Okay, notice that I just have here a voltage divider. Okay, if nothing is connected to V's of X, then effectively these two are in series and I have a voltage divider. So that V's of X, okay, V's of X, sorry about that. V's of X is just, since these are equal, okay, 1/2 of minus 15, no? Minus 15 over 2. So I'm going to get minus 7.5 volts. Okay, if I now apply minus 7.5 volts to this op amp, okay, what will I get? You're going to conclude that, okay, if the two were not connected, V out would be equal to, okay, so if the two not connected, if not connected, let me just say not connected, and minus 7.5 volts applied to the second stage, okay, then V out would be equal to, okay, your gain here is -2. So you have -2 multiplied by minus 7.5 and you're going to get, okay, 15 volts. But if I connect these two together, my answer is not going to be minus 15 volts. No? Why? No? So if the two were connected, however, V out is not going to be equal to minus 15 volts. No? Sorry about that. Why? No? Okay, why? Okay, what you're going to see here, Ri, is going to be Rx. No? Let me rewrite that. Okay, so inside here you're going to see Ri is equal to Rx, and that Rx is going to be in parallel with this 1K. That Rx is going to be in parallel with 1K. Okay, the input, okay, so let me write it. The input resistance of the second stage is in parallel with your 1K. So if I take a look, I'm going to have Ri here. Right? So you have 1K in parallel with 1K. No? Let me just redraw it so that it doesn't look so cluttered. No? Okay, so I have my 3 volts. This is 1K. This is 5K. I have 1K. Okay, this is V's of X. I have here 1K. And now here I have Ri. Okay. That is going to be the equivalent circuit. No? When these two are connected, that's going to be the equivalent circuit as seen by this particular op amp. Now we already know that V1 is equal to minus 15 volts. Okay, so what is Vx going to be? No? The parallel combination of these two, this is Ri is equal to 1K, this is 500 ohms. Okay, so what is Vx? Vx is now going to be V1 times 500 over 1K plus 500. Okay, so that's what's going to happen. No? So this is going to be equal to negative 5 volts. In other words, no, if this were separated, this voltage will be negative 7.5 volts. But the minute I connect these two together, this voltage is going to go down to negative 5 volts. And that's because of the loading effect of Rs of X. Okay, so finally, what is going to be my V out? That is going to be Vx times minus 2. No? My gain is minus 2 times Vx, right? The gain of this is minus 2. So I'm going to get 10 volts. Okay, so again, no, the takeaway here is you have to consider the loading effect an input to an op-amp might have on the output it is connected to. Okay, this is the last example, and this is an instrumentation amplifier. Okay, if you take a look at this particular circuit here, this is just the difference amplifier that we took up earlier, no? Where we said that, okay, we had R1, R2, R2, R1, R4, and R3, no? So R1 and R3 were made equal, so these are both now R1. R2 and R4 were made equal, so these are now both R2. Right? So this is our difference amplifier. Okay. Now what we added to our difference amplifier, what essentially was added to the difference amplifier, okay, is an input stage at the inputs to the difference amplifier that will make Ri for the input equal to infinity. Now, why is Ri going to be equal to infinity? No, because our inputs are connected to the a non-inverting input. No, so there is no current flowing here, and therefore this looks like an open circuit to V2. The same way, this looks like an open circuit to V1. Okay, so this is an improvement over your normal difference amplifier, because now your V2 and V1, okay, will not feel that anything is connected to it. Okay, so we know from our difference amplifier that V sub O, okay, from here, and we already derived this earlier, we know that V sub O is going to be R2 over R1, okay, V's of D minus V's of C, no? The voltage at this point minus the voltage at that point, no? Okay, that's here, no? We already derived that, no? For this particular circuit. No? Here it's V1 minus V2, no? That's the one connected to the non-inverting and to the inverting. So here it's VD minus V sub C. Okay, so what we have to do is we have to find expressions for V sub C and V sub D in terms of V1 and V2. Unfortunately, that is not very difficult. Okay, we can form two KCL equations to do that, no? Okay, just a question, no? Can you do a KCL at C, no? Okay. You cannot do a KCL at C because you have no idea what the output current is going to be. No? So I'll just write that down as a note, no? Note. You cannot do a KCL at C because we do not know the output current of the op-amp. And that is a very common mistake made by students. No? They get so used to the fact that the input current is 0 that they also think that the output current is 0. Note that this output current is not 0. So that makes it not useful to do a KCL at either C or D. No? So where we will apply KCL to would be A and B. No? So we do a KCL at A. Okay, if we do a KCL at A, okay, you have VA minus VC over R4. So that's your current here. And then you have VA minus VB over 2R3. Okay. So that's your current going down here. And then we know that this current is 0. So naturally, this will be equal to 0. Okay, but note, because this is an ideal op-amp, VA is equal to V2. No? Remember, you have a virtual short here. No? Virtual short here. You also have a virtual short here. No? So VA is equal to V2 and VB is equal to V1. Okay, so this is actually V2 minus VC over R4, okay, plus V2 minus V1 over 2R3 is equal to 0. I can now isolate V sub C. I can isolate V sub C. Okay, let me rewrite this. V2 minus VC over R4 plus V2 minus V1 over 2R3 is equal to 0. No? So I'm going to get V2 1 over R4 plus 1 over 2R3, okay, minus V1 over 2R3 is equal to VC over R4. Or VC is equal to R4 okay, multiplied by 1 over R4 plus 1 over 2R3 V2 minus 1 over 2R3 V1. Okay, so that's our expression for R4. Okay, let me just check, no? Minus V1 over 2R3 is equal to VC over R4. So VC, R4 goes on top. Yeah, okay. So let's also do a KCL at B. No? KCL at B. Okay. So we have VB minus VD over R4, VB minus VA over 2R3. No? VB minus VD over R4 plus VB minus VA over 2R3 is equal to 0. But again, we said that VA is equal to V2, VB is equal to V1. So this is going to be V1 minus VD over R4, okay, plus V1 minus V2, VA is equal to V2 over 2R3 this is equal to 0. Okay, if I solve for VD, the same way I solve for VC here, I can solve for VD. Okay, what am I going to get? I'm going to get VD is going to be equal to R4. Okay. Okay. Yeah. 1 over R4, okay, plus 1 over 2R3 multiplied by V1, okay, yeah, minus 1 over 2R3 multiplied by V2. Yeah, that's right, no? Okay, let me compute for VD minus VC. Because to get V sub O, I multiply VD minus VC by R2 over R1, no? So VD minus VC is equal to, okay, this term minus this term, no? Now notice that the R4 is just going to cancel, no? This R4 is going to cancel with this R4. What am I going to get? I'm going to get 1 over R4 plus 1 over 2R3 V1, okay, minus 1 over 2R3 V2, okay, minus 1 over R4 plus 1 over 2R3 V2, okay, minus 1 over 2R3 V1. Okay, yeah, that's right, no? Can we simplify this? Okay, this is going to be, okay, let's collect V1 terms together. Okay, this is going to be V1 multiplied by 1 over R4 plus 1 over 2R3 plus 1 over 2R3, okay? That's this, ano? Negative is plus 1 over 2R3, okay? Minus V2, okay? So let's consider this term. 1 over R4 plus 1 over 2R3, okay? Plus 1 over 2R3. Okay, so what am I going to get, ano? This is 1 over R4 plus 1 over R3. This is 1 over R4 plus 1 over R3. I'm going to get 1 over R3 plus 1 over R4 V1 minus V2. Okay. And so, finally, what is V sub O? Okay, V sub O is R2 over R1 let me just make sure I got this right, no? Sorry. I cannot cancel out. Sorry, no? I should not have I knew that there was something wrong. I shouldn't have cancelled out this R4, no? Because this is not equal to 0, no? So this is multiplied pa rin by R4. May R4 pa rin rito. No? So this whole thing is multiplied by R4. Okay, so this whole thing is multiplied by R4. So this is going to be 1 plus R4 over R3 multiplied by V1 minus V2. Sorry about that. Okay. That is VD minus VC. Okay, it looked like there was something wrong with it. Good, I caught it. No? Okay, so finally, what is V sub O? V sub O is R2 over R1, and then I'm going to get 1 plus R4 over R3. Okay, V1 minus V2. Okay, so that's it. No? That's the output of your instrumentation amplifier. I hope you're able to follow that. Okay, so that's my last example. In summary, you should now be comfortable analyzing op-amp circuits when the op-amp is assumed ideal. And you should be able to cascade op-amp circuits to synthesize simple functions. So you're not expected to synthesize very complicated functions yet. But you should be able to synthesize simple functions. Okay. And you were given some standard op-amp circuits, your inverting amplifier, non-inverting amplifier, inverting and non-inverting summer, the difference amplifiers. These are very standard building blocks. When you see that particular topology, actually you don't even have to derive anymore the output in terms of the input. Usually you already know it from familiarity with the topology. I included some exercises at the end of this particular module. 3 in fact. So exercise 1, this is a 3-bit digital to analog converter. I think the exercise is self-explanatory. Exercise 2, you're going to derive the relationship between the output and the input of, this is what is called a Sallen-Key filter topology. Okay. And then finally, some exercises on cascaded stages. So give these a try. That's it for this particular module. Thank you.